The entire universe glows with a faint, cold light from its violent birth. This is the cosmic microwave background, the oldest light we can see, a direct echo of the Big Bang itself. By the end of this journey, you will see the cosmos through an entirely new lens. We will explore how this echo was found by accident, why it holds blueprints for everything that exists, and what strange secrets it still keeps from us. What does it feel like to touch the edge of time? That faint cosmic whisper first reached human ears through sheer frustration. Two radio astronomers, Arno Penzias and Robert Wilson, were not looking for the beginning of time. They were simply trying to calibrate a sensitive new antenna at Bell Labs in New Jersey in 1964. Their goal was practical, to listen for faint radio signals bouncing off satellites. But their work was plagued by a maddening, constant hiss. It was a uniform static noise that came from every direction in the sky, day and night, and it would not go away. They checked every possible source of earthly interference. They pointed the giant horn-shaped antenna at New York City, thinking it was urban radio noise. Nothing changed. They even suspected the instrument itself, meticulously taking it apart and reassembling it. The hiss remained. In a now legendary move, they turned their suspicion to a pair of pigeons nesting inside the antenna. They thought the birds' droppings, which they described as a white dielectric material, might be causing the electrical noise. They trapped the pigeons, cleaned the antenna thoroughly, and even had the birds shipped far away. The pigeons stubbornly flew back, so Penzias and Wilson cleaned everything again, and still the relentless hiss persisted. It was an annoying, unsolved mystery, a flaw in their experiment they could not eliminate. What they did not know was that they were hearing the universe itself. That static was the cooled and stretched afterglow of the Big Bang, a signal that had been traveling for over 13 billion years to reach their antenna. While they were scrubbing pigeon waste, a team of theorists at Princeton University, just 40 miles away, was actively calculating how to find this exact signal, the predicted leftover heat from a fiery cosmic birth. When the groups finally connected, the truth became clear. The annoying noise was not a flaw. It was the foundation of everything. That frustrating hiss was the cosmic microwave background, the first solid evidence that our universe exploded from an incredibly hot, dense state. For discovering this echo of creation by complete accident, Penzias and Wilson were awarded the Nobel Prize in Physics. Their story is a beautiful reminder that sometimes the universe's greatest secrets announce themselves not with a fanfare, but with a persistent, puzzling whisper we almost tried to clean away. That persistent hiss they discovered was uniform, a perfect sea of static. But perfection in the cosmos is often a mask. When scientists finally developed the tools to look closer, they peeled back that mask to reveal a breathtaking truth. The cosmic microwave background is not perfectly smooth. It is covered in tiny, faint wrinkles. These are minute temperature fluctuations, areas that are ever so slightly warmer or cooler than the average by just a few millionths of a degree. Think of it like the surface of a calm pond on a windless day. From a distance, it looks like flawless glass, but if you could shrink yourself down to the size of an atom and float on that surface, you would see a delicate, rippling texture everywhere. Those ripples are the cosmic equivalent of a fingerprint, a unique pattern imprinted on the sky. And this fingerprint is not random noise. It is the most important blueprint in existence. Those tiny wrinkles are the seeds of everything we see in the universe today. The slightly denser, warmer spots in that ancient fog had a tiny bit more gravitational pull. Over billions of years, they acted as anchors, gathering more and more gas and dark matter around them. The cooler, emptier spots became the vast cosmic voids. From those microscopic imperfections grew the first stars, the swirling galaxies, the colossal clusters of galaxies that stretch across the heavens. You are looking at the origin point of all cosmic structure. To read this blueprint, we needed a map. The first mission to clearly see these wrinkles was NASA Cosmic Background Explorer, or COBE, launched in 1989. Its data revealed the universe's infant face for the first time, a mottled sky of primordial hot and cold spots. Scientists called it the moment they saw the face of God in the data. Later missions like the Wilkinson Microwave Anisotropy Probe, or WMAP, and Europe's Planck satellite drew this map with even finer detail, turning a blurry impressionist painting into a sharp, high-definition portrait of creation's dawn. So the next time you look up at a star-filled night, remember this: every galaxy, every star, every planet, and every one of us exists because the newborn universe was not perfect. We are all the children of cosmic wrinkles. This cosmic blueprint is also the coldest thing in the natural universe. Its temperature has been measured with astonishing precision at 2.725 Kelvin. To grasp what that means, you need to understand absolute zero. That is the theoretical point where all atomic motion stops, the ultimate cold at 0 Kelvin, or negative 273.15 degrees Celsius. The cosmic microwave background is just 2.725 degrees above that absolute floor. It is colder than the dark void between galaxies. It is colder than the deepest, emptiest reaches of intergalactic space, which still hold a faint warmth from stray starlight. It is even colder than the Boomerang Nebula, long considered one of the coldest known places, which is chilled by expanding gas to about 1 Kelvin. This pervasive, uniform chill is the key to its origin story. It is the cooled-down remnant of the universe's unimaginably hot infancy. Picture the moment of the Big Bang as a blinding, searing flash of heat. In the instant after, the entire cosmos was a dense, opaque soup of particles and energy, hotter than the core of any star. Then it expanded, and as it expanded, it stretched. Just as stretching a rubber band makes it cooler, stretching the fabric of space itself stretched the light within it. The brilliant, short wavelength light from that initial fireball has been stretched and stretched over 13.8 billion years, its waves pulled from the visible spectrum all the way down into the microwave band. That incredible journey from trillions of degrees to just a few degrees above absolute zero is written in its temperature. So when we measure that faint, cold glow, we are not just mapping the sky. We are taking the universe's temperature and reading the story of its great cosmic cooling on the grandest scale possible. This uniform cold blanket, however, holds a secret about our own motion. We are not sitting still within it. In fact, everything in our local cosmos, Earth, the Sun, our entire Milky Way galaxy, is racing through this ancient radiation at a staggering 1.3 million miles per hour. How do we know this? The cosmic microwave background reveals our speed through a phenomenon called the dipole anisotropy. It sounds complex, but the concept is beautifully simple. Imagine you are standing still in a gentle, perfectly even snowfall. The flakes fall on you evenly from all directions. Now start running forward through that snow. Suddenly, you are running into the flakes head-on. They appear to be coming at you faster from the direction you are moving, hitting your face more frequently. Meanwhile, from behind you, the flakes seem to be catching up to you more slowly. The cosmic microwave background photons are like that cosmic snowfall. Because we are moving at tremendous speed through this stationary sea of light, we measure it as slightly warmer or blue-shifted in the direction we are heading. The photons there are packed a little closer together, carrying a bit more energy from our perspective. In the opposite direction, the sky behind us, the light is stretched and redshifted, appearing ever so slightly cooler. This creates a hot spot and a cold spot in the map of the sky, a cosmic temperature difference of about 1/100th of a degree. It is a tiny imprint, but by measuring it, scientists can calculate our velocity. That velocity is roughly 370 kilometers every single second. We are cosmic speedsters on an epic journey, and the oldest light in existence is how we clock our speed. This motion is not just the Earth orbiting the Sun. It is the Sun orbiting the galactic center and the entire Milky Way being pulled by the gravitational titans around us. We are caught in a vast flowing river of galaxies, so that uniform background is also a compass pointing out our direction of travel through the expanding universe. Our motion through this ancient light reveals a universe in flux, but the light itself settled one of the greatest debates in science. Before its discovery, cosmology was a battlefield of ideas. The dominant theory was the Big Bang, proposing a definite, fiery beginning, but it had a formidable rival, the steady-state theory. This elegant idea suggested the universe had no beginning and no end. It was infinite in time, always looking roughly the same on the largest scales. To explain the obvious expansion we observe where galaxies are flying apart, steady state proposed a radical fix. It said new matter was constantly being created ex nihilo, out of nothing, in the empty spaces between galaxies. Just a few atoms per cubic kilometer every century, enough to fill the gaps and keep the cosmic density constant forever. A universe with no origin story, an eternal, unchanging tapestry. It was a beautiful, philosophically comforting idea, but it made a critical prediction, or rather, a lack of one. In a steady-state universe, there could be no leftover glow from a hot, dense past, because there never was a hot, dense past. The cosmos was always cool and rarefied. So when Penzias and Wilson stumbled upon that pervasive microwave hiss, and it was identified as the cooled remnant of a primeval fireball, the steady-state theory had a fatal problem. This was not a minor anomaly. The cosmic microwave background was a direct smoking gun prediction of the Big Bang model. Theorists like George Gamow had calculated decades earlier that if the universe began in a hot, dense state, it should be filled with this cool afterglow. The CMB was that prediction made real. The steady-state theory had no convincing way to explain it. You cannot have a relic from a beginning if you insist there was no beginning. The discovery did not just support the Big Bang, it buried its rival. It was the final, undeniable piece of evidence that shifted our cosmic paradigm forever. We lived not in an eternal, steady universe, but in one that had a dramatic birth, and whose faint, cold echo still surrounds us, the definitive signature of our explosive origin. The Big Bang's echo gives us more than just a speedometer, it is a time capsule. This is not a fuzzy picture from the distant past. It is a precise, momentous snapshot of the universe at exactly 380,000 years old. To understand why that age is so special, we must journey back to a time before stars, before galaxies, before atoms as we know them. In its first few 100,000 years, the cosmos was an inferno. It was so hot and dense that the basic building blocks of matter, protons and electrons, could not stick together. They were ripped apart as fast as they tried to combine. These free, charged particles turned the universe into a thick, blinding fog. Light could not travel in a straight line. A photon would be born, zip a tiny distance, and then smash into a free electron, scattering in a new direction. It was trapped like a person lost in a blinding whiteout blizzard, unable to see more than a few feet ahead. The entire universe was this opaque, glowing plasma. Then expansion did its work. As space stretched, the energy within it diluted and cooled. By the time the universe celebrated its 380,000th birthday, the temperature had dropped to about 3,000 Kelvin. That is still scorching hot, like the surface of a cool star, but it was cool enough for a fundamental change. Protons could finally capture those free-flying electrons. They combined to form the first stable atoms of neutral hydrogen. This pivotal event is called recombination. In an instant, on a cosmic scale, the fog lifted. With the electrons now bound up in atoms, the highways of the universe were suddenly clear. The light that had been trapped, bouncing around for millennia, was finally set free. That first flash of liberated light is what we see today as the cosmic microwave background. we are witnessing the moment the universe became transparent. It is the afterimage of the last scattering surface, the final wall of the primordial plasma. Every photon in that ancient light has been traveling in a straight line toward us ever since that single definitive moment. So when we map the CMB, we are not looking at a gradual process. We are looking at a fossilized instant, a baby picture of the cosmos taken on the very day it opened its eyes for the first time. That baby picture of the cosmos is not delivered overnight. It arrives by the slowest postal service in existence, the light from that last scattering surface, released when the universe was a mere 380,000 years old, has been on an epic journey to reach your eyes. It has been traveling through the expanding void for over 13.8 billion years. To put that timescale into perspective, when that photon began its voyage, our sun did not exist. Our Milky Way galaxy was just beginning to coalesce from primordial gas. Every star you see at night, every planet, every mountain and ocean on Earth, all formed long after this ancient messenger was already on its way. By the time it finally enters a telescope like Planck or WMAP, it has crossed almost the entire breadth of the observable universe. This is what makes the cosmic microwave background the ultimate time machine. When we point our instruments at it, we are not looking out into space in the conventional sense. We are peering directly back in time to the very edge of what is possible to see. There is nothing beyond it, because before that moment the universe was opaque. It is the final curtain, the deepest fossil layer. We are looking back to a time before the first stars flickered on, before galaxies swirled into being, to the universe's dark, simple childhood. Every other object we observe, no matter how distant, is younger than this. A galaxy 10 billion light-years away is a snapshot of the universe at age 3.8 billion years, already mature and structured. The CMB shows us the newborn, so this faint glow is more than an echo. It is a letter written in the language of microwaves, mailed from the dawn of time, and it has only just now, after a journey lasting nearly the entire age of the cosmos, dropped into our mailbox. That letter from the dawn of time was written in a different language entirely. The light released at the moment of recombination was not a faint microwave whisper. It was a brilliant, searing glare. The universe at that moment glowed with the intense, white-hot light of a plasma at 3000 Kelvin. To the eyes of any hypothetical observer back then, the entire sky in every direction would have shone with the blinding orange-white radiance of a trillion suns. So how did that ferocious blaze become the feeble, cold glow we detect today? The answer is written in the sound of a passing siren. You have heard the Doppler effect. When an ambulance races toward you, its siren sounds high-pitched. As it passes and speeds away, the pitch drops dramatically. The sound waves are literally stretched by the motion, becoming longer and lower in frequency. The universe is doing something similar to light, but on a cosmic scale. This is called cosmological redshift. Space itself is expanding, stretching the very fabric between galaxies. As light travels across this expanding gulf, its waves are stretched along with the space they move through. The longer the journey, the more stretching occurs. That primordial fireball light has been on a journey of over 13 billion years. In that time, the universe has expanded by a factor of about 1,100. The wavelength of its light has been stretched by that same enormous factor. Imagine taking a vibrant, visible red light wave and pulling it like taffy until it is over 1,000 times longer. It is no longer visible. It has been redshifted all the way down the electromagnetic spectrum, through infrared and into the microwave band. This is why we cannot see the cosmic microwave background with our eyes or optical telescopes. Our eyes are tuned to the original, unstretched light. To see this stretched relic, we must use instruments that hear the universe in radio waves, like giant ears listening to the deepest bass note the cosmos can sing. That faint hiss Penzias and Wilson heard was the stretched, faded echo of the universe's first and brightest dawn. This stretched light is not just a whisper from a single point in the sky. It is everywhere, no matter where you point the most sensitive radio telescope on Earth or one floating in the quiet of space. You will detect the same faint, cold signature of the cosmic microwave background. It is the ultimate background, a literal canvas upon which every star, every galaxy, and every nebula is painted. This omnipresence is its most profound feature. It means that if you could see in microwaves, your entire field of view, from horizon to horizon, day and night, would be filled with this gentle, uniform glow. There is no hiding from it, and no place in the universe is untouched by it. It is the foundational hum of reality itself. This fact creates a startlingly intimate connection to the cosmos. For decades, many of us experienced this echo of creation without ever knowing it. On an old-fashioned analog television set, when you tuned to a channel that had no broadcast signal, you would see a chaotic dance of black and white static. That snow, that frantic hiss, was not all random electronic noise. Roughly 1% of that flickering chaos was directly caused by photons from the cosmic microwave background raining down on your television antenna. Think about that. In the quiet moments of changing channels, perhaps late at night, you were not just seeing interference. You were witnessing with your own eyes in your own living room the cooled remnant of the Big Bang itself, translated into a grainy, monochrome pattern on a glass screen. It was a secret broadcast from the beginning of time, playing on a loop in the background of everyday life. That static was the universe's oldest story, quietly insisting on being heard amidst the mundane. So this echo is not locked away in distant observatories. It is woven into the very fabric of our reality, a background so complete and so constant that for a time, it literally provided the background to our evening entertainment, a cosmic secret hiding in plain sight. That secret broadcast from the beginning of time carries a hidden message about the shape of all reality. The pattern of those tiny wrinkles, the hot and cold spots, is more than a blueprint for galaxies. It is a cosmic ruler, a way to measure the very geometry of the universe itself. Think about geometry on a grand scale. If you could draw two perfectly parallel laser beams and send them across the cosmos, what would happen to them? Their fate would reveal the universe's shape. In a closed, spherical universe like the surface of a balloon, those parallel lines would eventually converge and cross. In an open, saddle-shaped universe, they would diverge, spreading apart forever. But in a flat universe, the kind we learn about in school, those lines would remain parallel, extending into infinity without ever meeting or bending away. The size of the hot and cold spots in the cosmic microwave background gives us the answer. When the universe was young and small, sound waves raced through the primordial plasma. These were not sound waves in air, but vast pressure waves like ripples in a cosmic pond. They had a maximum distance they could travel before the universe became transparent, a sort of sonic horizon. This distance imprinted a preferred size, a characteristic scale, onto the wrinkles we see in the CMB. It is like a frozen echo of the loudest note the young universe could sing. By measuring the apparent angular size of these spots on our sky, we can deduce the geometry. If the universe were positively curved like a sphere, the spots would appear larger to us. If it were negatively curved like a saddle, they would appear smaller. The data from missions like WMAP and Planck is unequivocal. Those spots appear exactly the size predicted for a flat universe. The parallel lines on the largest imaginable scales stay parallel. This is a staggering result. It means that the familiar rules of Euclidean geometry, the ones you learned about triangles and parallel lines, hold true not just in your classroom, but across the entire observable cosmos. The universe, in its overall structure, is flat. This flatness is not a trivial fact. It is a profound clue about the total density of the cosmos, a delicate balance between matter, energy, and the expansion rate, set with unbelievable precision in the first moments of the Big Bang. This precise geometry offers us more than just a shape. It hands us the universe's complete recipe. By meticulously analyzing the pattern of those primordial wrinkles, cosmologists have performed the ultimate cosmic audit. They have measured the exact composition of everything that exists, not by weighing galaxies directly, but by reading the subtle imprints left in the infant universe's light. The result is a pie chart of reality, and its numbers are profoundly humbling. The stuff we know and love, the atoms that make up every star, every planet, every mountain, tree, and person, accounts for a mere 5% of the total cosmic budget. All the visible, tangible universe is just a thin sprinkling of luminous dust in a vast, dark sea. The remaining 95% is invisible and deeply mysterious. About 27% is dark matter. We cannot see it because it does not emit, absorb, or reflect light, yet its presence is undeniable. Its gravitational pull is the invisible scaffold that holds fast-spinning galaxies together, preventing them from flying apart. It is the cosmic glue that shaped the large-scale structure we see today, acting as the gravitational anchor around which ordinary matter could gather. But the majority, a staggering 68% of the entire cosmos, is something even more enigmatic: dark energy. This is not matter at all, but a property of space itself, a repulsive force that is causing the expansion of the universe to accelerate. It is the dominant component of reality, and we understand it the least. How do we know these precise percentages: 5, 27, and 68? The cosmic microwave background tells us. The size and distribution of its hot and cold spots are exquisitely sensitive to how much ordinary matter, dark matter, and dark energy were present in the early universe. The patterns we see are the frozen result of a tug of war between gravity, which tries to pull matter together to make bigger wrinkles, and radiation pressure, which tries to smooth everything out. By matching the observed pattern to detailed computer models, scientists can dial in the ingredients until they find the perfect fit. The cosmic microwave background is the ultimate forensic accountant, examining the universe's first financial records to give us a balance sheet for all of creation. We are not the main characters in this cosmic story. We are a rare and interesting footnote, living in a universe dominated by forces we are only beginning to name. This cosmic recipe, however, comes with a few strange ingredients we cannot yet explain. For all its remarkable uniformity, the map of the cosmic microwave background is not perfectly boring. It contains peculiar anomalies, features that stand out and stubbornly refuse to fit our neat models. The most famous of these is known simply as the CMB cold spot. Located in the constellation Eridanus in the southern sky, it is a vast circular region of space that is significantly colder than the surrounding background. We are not talking about a tiny dip. This spot is enormous, spanning nearly 1 billion light-years across, and it is about 70 microkelvin colder than the average. That may sound trivial, but on such a colossal scale, it is a glaring outlier. If the cosmic microwave background is a serene, humming note, the cold spot is a sudden, deep silence in the middle of the symphony. So what could possibly create such a bizarre feature in the universe's oldest light? Scientists have proposed several intriguing and some truly mind-bending explanations. The simplest idea is that it is just a colossal statistical fluke. In any random dataset, even a perfectly normal one, you can occasionally get a result that looks wildly improbable by pure chance. It could be that we are simply the unlucky observers in a cosmic lottery, living in a place where the primordial wrinkles just happen to form one giant cold patch. But the odds of such a fluke are incredibly low, making many researchers search for a physical cause. One leading theory points to a giant supervoid. Imagine a region of space that is unnaturally empty, a cosmic desert spanning hundreds of millions of light-years with far fewer galaxies and clusters than expected. If such a void existed between us and the cold spot, It could theoretically create the cold imprint through a process called the integrated Sachs-Wolf effect. As light from the CMB passes through an underdense region, it must climb out of a shallower gravitational well, losing a tiny bit of energy and thus appearing slightly colder. But to produce the cold spot we see, this void would need to be staggeringly large and empty beyond anything we have observed elsewhere. Then there is the most speculative and most thrilling possibility. Some cosmologists suggest the cold spot could be a bruise, a remnant of a collision with another universe. In certain theories of a multiverse, our universe is one bubble among many in a frothing cosmic foam. If, during its early expansion, our bubble universe grazed another, the energy of that collision could have left an imprint on our sky, a circular scar of distorted spacetime that appears as a cold spot in the radiation. It is a hypothesis that is nearly impossible to test directly, but it captures the imagination, hinting that our entire cosmos might bear the mark of a long-ago encounter with a reality beyond our own. For now, the true nature of the cold spot remains an open question, one of the most tantalizing active mysteries in modern cosmology. It is a reminder that even our most precise map of creation still has blank spaces labeled "Here be dragons." These strange anomalies challenge our maps, but the cosmic microwave background's most profound validation came from a theory that seemed like science fiction. The universe's overall flatness and its stunning uniformity, that same temperature across opposite sides of the sky, presented a colossal puzzle. How could regions billions of light years apart, which could never have exchanged heat or information, be so perfectly in sync? It was as if two strangers on opposite sides of the planet were wearing the exact same outfit, down to the scuff on their left shoe, without ever having met. This horizon problem demanded a radical solution. The answer, proposed in the 1980s, is cosmic inflation. This idea suggests that in the first incomprehensibly tiny fraction of a second after the Big Bang, the universe underwent a burst of exponential expansion. Space itself inflated faster than the speed of light, doubling in size over and over again in intervals as short as a trillionth of a second. This violent growth spurt took a minuscule, causally connected patch of the primordial cosmos and stretched it to a size larger than our entire observable universe today. That is why everything looks so uniform. The entire sky we see was once a tiny, homogeneous neighborhood that had time to even out its temperature before being blown up to cosmic proportions. Inflation also explains the flatness. Imagine taking a tiny, wrinkled crinkle from the surface of a balloon and inflating it to the size of a house. That small section would appear perfectly flat to an ant crawling on it. Inflation did the same to the geometry of spacetime, stretching any initial curvature into the flat universe we measure. The cosmic microwave background provides the smoking gun for this incredible event. One key piece of evidence is a specific pattern imprinted on the light's polarization, a property describing the orientation of its waves. Inflation's violent stretching of spacetime would have created gravitational waves, ripples in the fabric of reality itself. These waves would have left a distinctive swirling pattern called B-mode polarization in the CMB. While the signal is incredibly faint and contested, the hunt for it is one of the most intense pursuits in cosmology. Finding it would be like discovering the fossilized footprints of the universe's first and most dramatic step. So the next time you hear about the Big Bang, remember it was likely preceded by something even more explosive. A growth spurt so fierce it set the stage for everything to come, and its echo is still written in the cold, ancient light that surrounds us. That echo of inflation is literally frozen into the fabric of the cosmic microwave background, but it is not a silent picture. It is a sonic fossil. To understand this, we must listen back to the universe before it became transparent during those first 380,000 years. It was not a quiet, empty place. It was a seething, dense, and incredibly loud plasma, a roiling soup where light and matter were locked in a constant, violent dance. Photons could not travel freely because they were constantly slamming into free electrons. This tight coupling meant that light and matter behaved as a single fluid, a glowing, pressurized fog. And in any fluid under pressure, you get sound waves. These were not sound waves as we know them, vibrations in air. They were pressure waves in the primordial plasma itself, vast spherical ripples propagating outward from every slight overdensity, like the booming echoes in a cosmic bell. Gravity would try to pull matter inward, clumping it together, while the intense radiation pressure from the trapped photons would push it back outward, creating a rhythmic push and pull. This set the entire universe ringing. For nearly 400,000 years, these acoustic oscillations reverberated through the cosmos, a deep, fundamental hum of creation. Then, at the moment of recombination, the music stopped abruptly. When atoms formed and the fog cleared, the photons were set free, and the matter was left behind, frozen in place. The waves in the fluid were instantly fossilized. The cosmic microwave background's temperature map is a recording of that final, frozen instant. The pattern of hot and cold spots we see is not random. It is the imprint of those standing sound waves at the moment the music ceased. The slightly hotter spots are where the plasma was compressed, the peaks of the sound waves. The slightly cooler spots are where it was rarefied, the troughs, and there is a most important scale. The largest, most common size of these spots corresponds to the distance a sound wave could travel in the universe's first 380,000 years. Think of it as the cosmic sonic horizon, the farthest a single note could have reached from its origin before the universe went silent. This distance became a fundamental ruler etched into the sky. By measuring the angular size of these spots, we are literally measuring the wavelength of the universe's first and deepest note, a bass note so profound it set the scale for all cosmic structure to come. So the cosmic microwave background is more than a baby picture or a temperature map. It is a phonograph record of the universe's infancy, and we are just now learning how to play it. This sonic fossil is not just for our eyes to analyze, it is for our ears to hear. Scientists have performed a remarkable act of translation, turning the cold, silent map of the cosmic microwave background into sound. They have taken the temperature data, the precise measurements of those hot and cold wrinkles, and assigned different musical pitches to different temperatures. A slightly warmer spot might become a slightly higher note, a cooler spot a deeper tone. Scanning across the map, they sonified the sky. What emerges is not a melody, but something far more profound. It is a deep, rumbling, otherworldly chorus, a low drone punctuated by shifting harmonics. This is the literal sound of the early universe's density fluctuations, the pressure waves in that primordial plasma, translated into a range our ears can perceive. It is haunting and alien, like the groan of a colossal iceberg calving into a dark sea, stretched across billions of years. Listening to it, you are not hearing sound waves traveling through space, as space was too empty for that after recombination. Instead, you are hearing the pattern of creation itself converted into an auditory experience. This is the universe's first cry, captured in a snapshot and given a voice. It is the vibrational signature of the seeds that would become galaxies, rendered into a form that bypasses our intellect and speaks directly to our senses. To hear it is to feel, in a visceral way, the immense and turbulent forces at play in our cosmos's first moments, a direct connection to the deep past that is as emotional as it is scientific. That deep hum of creation provides more than a history lesson. It serves as a cosmic speedometer. By analyzing the cosmic microwave background with exquisite precision, scientists can calculate a fundamental number, the Hubble constant. This is the rate at which the universe is expanding today, a single figure that tells us how fast galaxies are rushing apart from one another. The CMB gives us a unique way to find it. We start with that pristine snapshot of the infant universe, with all its detailed wrinkles and precise geometry. We know the physics of that early plasma extremely well. Cosmologists then run the cosmic film forward in their supercomputers. They apply our standard model of cosmology, which includes all the ingredients like dark matter and dark energy, and simulate how those tiny wrinkles should grow over 13.8 billion years into the galaxy clusters we see today. The model predicts how fast the universe must have been expanding to make everything line up perfectly between that ancient map and our modern night sky. From this, they derive a value for the current expansion rate. It is an incredibly powerful method because it uses the entire observable universe as its laboratory. The result from the Planck satellite is breathtakingly precise, 67.4 kilometers per second per megaparsec. This means for every additional megaparsec, a distance of about 3.3 million light-years, a galaxy appears to be moving away from us 67.4 kilometers per second faster. It is a cornerstone of modern cosmology derived from the echo of the Big Bang itself. But here is where the story takes a dramatic turn. There is another, more direct way to measure the Hubble constant. Astronomers look at relatively nearby galaxies within a few hundred million light-years. They use brilliant stellar explosions called Type I, a supernova, as standard candles, objects of known intrinsic brightness. By measuring how dim they appear, we can gauge their distance. Then, by measuring how much their light is redshifted, we know how fast they are receding. This is like measuring the universe's current expansion speed with a radar gun, watching galaxies move in real time. This method, refined over decades, gives a different answer, around 73 kilometers per second per megaparsec. The numbers are close, but the uncertainty in each measurement is so small that they do not overlap. This is not a minor discrepancy. It is a glaring, persistent gap that has withstood years of rechecking and improved observations. Cosmologists call it the Hubble tension. Think of it like two supremely accurate clocks. One is built from the universe's first moments, the other from its present-day behavior. They are both exquisitely crafted, but they tick at undeniably different rates. This tension is not just a statistical fluke, it is a crisis. It strongly suggests that our otherwise incredibly successful standard model of cosmology, the very model that perfectly describes the CMB, is incomplete. We might be missing a key ingredient from our cosmic recipe. Perhaps dark energy is not constant but changing over time. Maybe there is a new, unexpected type of neutrino or a subtle property of dark matter. The Hubble tension is the most significant puzzle in modern cosmology, a direct challenge whispered to us by the ancient light. It tells us that the universe's expansion story, written in both its first echo and its present motion, contains a chapter we have not yet learned to read. That Hubble tension is a profound crack in our cosmic model, but it is not the only one. Another anomaly stares back at us from the map of the ancient light, one so unsettling that scientists gave it a dramatic nickname, the axis of evil. This is not about malevolence, but about a potential violation of a sacred rule in cosmology, the cosmological principle. This principle states that on the largest scales, the universe is isotropic and homogeneous. It should look the same in every direction, with no special places and no preferred axis. The cosmic microwave background is the ultimate test of this idea, and for the most part it passes with flying colors. Its temperature is stunningly uniform, yet when researchers began to look at the patterns of the hot and cold spots with advanced statistical tools, they noticed something strange. The fluctuations, those tiny wrinkles, did not appear to be completely random. They seemed to show a subtle alignment, a preferential direction, as if the entire pattern of the infant universe was slightly tilted along a specific axis that runs through our solar system. It is as if you laid out 1,000 compass needles randomly on a table, and instead of pointing in all directions, they all tilted slightly toward the northeast. This apparent alignment defies our expectation of perfect randomness. The cosmological principle demands that the universe have no center and no edge, no up or down. An axis of alignment would be like finding a giant, invisible arrow painted across the cosmos, suggesting a large-scale structure or orientation we do not comprehend. Some analyses even suggest that the quadrupole and octupole moments, which are specific mathematical descriptions of the large-scale patterns in the map, are aligned with each other and with the plane of our own solar system. This is deeply suspicious. It could be a real, physical feature of the universe, implying a fundamental anisotropy woven into the fabric of reality from the beginning. Or, more worryingly for cosmologists, it could be a sign of contamination, a subtle systematic error in how we process the data or account for our own motion through the cosmos. Perhaps it is even an echo of something in our local environment, like dust in our own galaxy, imprinting itself on the pristine signal. The truth is, the statistical significance of the axis of evil is debated. It sits in that uncomfortable zone where it is too prominent to ignore easily, but not strong enough to declare a definitive discovery, yet its persistence is a nagging worry. If it is real, it would mean our universe is not just a featureless, expanding bubble. It has a spine, a preferred direction that challenges a core pillar of modern cosmology and hints that our place in the cosmos might not be as ordinary as we thought. The universe's silent symphony is not a permanent broadcast. That ancient light, the cosmic microwave background, is slowly fading. Its temperature is not a fixed number etched in stone, it is a clock winding down. Right now, it sits at 2.725 Kelvin, but that number is falling. As the fabric of space continues to stretch, every photon in that sea of radiation is being pulled a little thinner, its wavelength lengthened by the relentless expansion. This is the ultimate cosmological redshift in action, a process that never stops. Each billion years that passes, the universe grows larger, and the echo of its birth grows colder and fainter. It is a direct, inevitable consequence of living in an expanding cosmos, the slow cooling of the universe's residual fever from its explosive beginning. To understand where this leads, we must project our gaze into the almost incomprehensible future. Imagine a time trillions of years from now when the universe is many times its current size. The cosmic microwave background will have redshifted so dramatically that it will no longer be in the microwave part of the spectrum. Its photons will have been stretched into long, lazy radio waves, carrying so little energy that they will blend into the background noise of the cosmos, becoming virtually impossible to distinguish. For any astronomers in that distant era, the most important piece of evidence for the Big Bang will have vanished from their skies. The universe will appear silent, cold, and dark, with no obvious sign of its fiery origin. The afterglow of creation will have dissipated entirely, like the last warmth fading from a stone long after a campfire has turned to ash. This is not speculation, it is the inescapable physics of an expanding universe. The very phenomenon that allows us to detect this echo today, the stretching of light, ensures that one day it will stretch beyond our ability to perceive it. We are living in a privileged cosmic moment, a brief window in the multi-trillion-year life of the cosmos where the universe is still young enough to bear the clear, detectable scar of its birth. We can still hear the echo. For civilizations that might arise in the far future, that evidence will be gone, lost to the endless stretching of space. The story of the Big Bang, so obvious to us, could become a forgotten legend, a theory without its most crucial proof. So when we map the CMB today, we are not just doing science. We are preserving a memory for the cosmos itself, capturing the fading signature of a dawn that will one day disappear from view entirely. The fading of this echo into the far future makes its discovery in our time feel even more remarkable, but that discovery was not entirely accidental. The cosmic microwave background was not just found, it was foretold. Decades before Penzias and Wilson scrubbed their antenna, a brilliant team of theorists had already written the script. In the 1940s and 50s, physicist George Gamow and his students Ralph Alpher and Robert Herman were working on a monumental puzzle, the origin of the elements. They were calculating how the universe could have cooked up the first hydrogen and helium in the fiery furnace of the Big Bang, a process we now call Big Bang nucleosynthesis. As they traced the physics of that expanding, cooling fireball, they reached a stunning logical conclusion. If the universe began hot and dense, then filled with radiation, that radiation would not have just vanished. As space expanded, that light would have cooled, but it would still be here, all around us, a cold relic permeating all of space. They didn't just predict its existence, they put a number on it. From their equations, Alpha and Herman estimated this leftover glow would have a temperature of about 5 Kelvin. That is just a couple of degrees warmer than the actual value of 2.725 Kelvin we measure today, a triumph of pure theoretical reasoning. Yet for all its brilliance, this prediction faded into obscurity. Their papers were published, but the technology to detect such a faint microwave signal did not yet exist. The astronomical community, still debating between the Big Bang and steady-state models, largely overlooked this specific forecast. The prediction became a forgotten footnote, a ghost in the equations, waiting for the right moment to step into reality. That moment came in 1964, when two frustrated radio engineers heard a hiss they could not explain. Only after Penzias made a phone call to a colleague did they learn of the Princeton group's search for this very signal, and the long-dormant work of Gamow, Alpher, and Herman was suddenly resurrected. This is the beautiful symmetry of science, a story of prophecy and serendipity intertwined. The theorists had drawn a map to a hidden treasure from their desks, using only mathematics and logic. The experimentalists, unaware of the map, tripped over the treasure while looking for something else entirely. When they compared notes, the universe's deepest secret was unlocked. It stands as a powerful testament to the human mind's ability to reach into the unknown, to predict the echo of creation itself, and then to have the humility to recognize that echo when it finally whispers back from the sky. That fading echo is also a cosmic detective, hunting for ghosts from the universe's birth. Beyond the familiar wrinkles, scientists scour the cosmic microwave background for stranger, sharper imprints, evidence of physics so exotic it borders on the surreal. One of the most sought-after phantoms is the cosmic string. Imagine the universe cooling from its initial, unified state, like water freezing into ice. When water freezes, imperfections can form, cracks and boundaries between different crystal structures. The cosmos may have undergone similar phase transitions in its first moments as fundamental forces split apart. These violent shifts could have created defects frozen into the fabric of spacetime itself. A cosmic string would be a one-dimensional crack, an infinitely long, unimaginably thin filament of pure energy, thinner than a proton but with the mass of a mountain range packed into every mile. It is a flaw in reality, a scar from when the universe's rules were still setting. Such an object would be so dense it would warp spacetime around it with incredible gravity. This is where the cosmic microwave background becomes our most sensitive instrument. As light from the CMB passes near a cosmic string, the severe warping of space would act like a cosmic lens, but with a unique signature. It would create a very sharp, discontinuous step in the temperature of the background radiation, a clean line across the sky where the temperature jumps abruptly from one side to the other. It would be a rip in the smooth tapestry, a telltale clue of a thread of primordial energy slicing through the cosmos. While such a dramatic feature has not yet been found, its possible imprint keeps researchers meticulously analyzing every new map. The search extends to other theoretical relics like textures or domain walls, each predicted to leave its own distinct fingerprint in the ancient light. So the CMB is more than a record of what was. It is a net cast into the deep past, trawling for the shadows of entities that might have shaped reality in ways we are only beginning to dream of. That search for cosmic strings uses the ancient light as a backlight, revealing the invisible. But the cosmic microwave background does more than hunt for ghosts, it casts shadows of its own. These are not shadows of darkness, but shadows of energy, and they are created by the most massive structures in the modern universe, galaxy clusters. When the pristine photons from the cosmic microwave background continue their billion-year journey, they must pass through everything in their path. Sometimes that path leads them directly through a colossal galaxy cluster. These clusters are not just collections of stars, they are immersed in a vast sea of incredibly hot gas, plasma heated to millions of degrees. As the cold, ancient CMB photons fly through this seething inferno, they do not pass through untouched. They collide with the energetic electrons whizzing around in the hot gas. In these collisions, the photons get a kick, a tiny boost of energy from the fast-moving electrons. This process is called the Sunyaev-Zeldovich effect, named for the two astrophysicists who predicted it. The result is a subtle but measurable distortion imprinted on the cosmic microwave background. In the precise direction of a massive galaxy cluster, the CMB appears slightly different. The low-energy microwaves get boosted to slightly higher energies. From our perspective, this creates a tiny, cold shadow in the original microwave light, a slight dip in temperature while simultaneously creating a bright spot at higher frequencies. It is as if you shone a pure, white light through a pane of tinted glass that selectively dims one color and brightens another. This shadow is incredibly faint, but it has a revolutionary property: it does not get fainter with distance. Whether a galaxy cluster is relatively nearby or at the edge of the observable universe, the strength of its Sunyaev-Zeldovich shadow is roughly the same. This makes it a phenomenally powerful tool for discovery. Traditional optical telescopes struggle to find the most distant clusters because their light is extremely faint and redshifted. But by scanning the cosmic microwave background for these characteristic shadows, astronomers can find massive clusters purely by the imprint they leave on the ancient light. It is like finding islands in a vast ocean, not by seeing the islands themselves from afar, but by spotting the distinctive shadows they cast on the ocean floor. This technique has already catalogued thousands of previously unknown clusters, building a census of the universe's largest structures across cosmic time. So the cosmic microwave background is not just a fossil to be studied in isolation. It is an active screen, and the universe's modern giants are constantly projecting their faint, energetic silhouettes upon it. These shadows cast by galaxy clusters are written in the language of light, but the cosmic microwave background is not the only ancient whisper in the void. It is the most famous fossil, but it belongs to a family of cosmic backgrounds, each telling a story from a different, more remote epoch. The CMB is the afterglow from when the universe was 380,000 years old. But if we could listen with even more exotic senses, we would hear echoes from far earlier chapters. Just 1 second after the Big Bang, when the cosmos was still a seething broth of fundamental particles, another monumental event occurred. The universe expanded and cooled enough for neutrinos, those ghostly particles that barely interact with anything, to stop interacting with the rest of the cosmic plasma. They decoupled, flying free into the expanding darkness. This created a cosmic neutrino background, or CNB. Picture it as a sea of the lightest, most elusive particles, streaming through everything at nearly the speed of light. Billions of these cosmic neutrinos pass through your thumbnail every second, a relic flood from the universe's first heartbeat. This background is far colder and even more challenging to detect than the CMB, as neutrinos slip through matter like ghosts through walls. Yet its existence is a firm prediction of our standard model, and catching even an indirect hint of it would give us a snapshot of the cosmos at the tender age of 1 single second, a time of unimaginable energy long before atoms or even atomic nuclei could form. Then there is the most speculative echo of all, the potential cosmic gravitational wave background. This would not be made of light or particles, but of ripples in spacetime itself, generated by the violent throes of cosmic inflation in the first fraction of a second. It is the faint, ringing tremor of spacetime, a hum left over from the universe's most explosive growth spurt. Detecting this background is the ultimate goal for next-generation observatories, as it would provide direct evidence for inflation and a window into energy scales we can never hope to recreate. So the cosmic microwave background is not a solo performer. It is the lead singer in a cosmic choir, the one we can hear most clearly. Behind it, there is the faint, ghostly harmony of the neutrino sea, and perhaps if we listen very carefully with the right instruments, the deep, foundational bass note of spacetime's own vibration. Each fossil radiation is a page from a different moment in the universe's infancy, and together they would tell the complete story of creation from its very first instant. The hunt for cosmic strings and other relics is a search for the universe's hidden architecture. But what if the most profound secret is not hidden within our universe but beyond its borders? The cosmic microwave background might be our only window into a reality even vaster and stranger than we have dared to dream, a multiverse. This is not science fiction, but a serious, though speculative, extension of our best theories. The leading model of cosmic inflation, which so perfectly explains the CMB's uniformity and flatness, naturally suggests a staggering possibility. If our universe underwent that exponential growth spurt, forming a bubble of stable spacetime, what is to stop that process from happening again and again and again? In this view, the greater cosmos is a frothing, bubbling sea of false vacuum energy, endlessly giving birth to new bubble universes, each with its own random set of physical laws and constants. We would inhabit just one of these countless bubbles, forever isolated from the others by walls of inflating space that expand faster than light. This is the multiverse hypothesis. If true, we could never visit another bubble, never send a probe, never receive a signal. They would be forever beyond our causal horizon. Yet there is one tantalizing, almost poetic possibility for contact. In the chaotic foam of the early multiverse, our infant bubble might not have inflated in perfect isolation. It could have jostled against a neighboring bubble as both expanded. The energy of that collision, a titanic clash of spacetime domains, would have sent shockwaves rippling through our newborn cosmos, and those shockwaves could have left an imprint, a bruise, frozen into the fabric of the cosmic microwave background. This brings us back to those eerie anomalies like the famous cold spot. Could that vast, inexplicably cold region in the constellation Eridanus be the scar of a long-ago encounter with another universe? The idea is that the collision would have drained energy from our region of space in a specific way, leaving a distinct circular pattern of cooler temperature in the CMB. It is a breathtaking thought. That faint, cold patch on our map of creation might not be a statistical fluke or a giant void. It could be a fossilized impact crater from a collision between realities. Other, more subtle statistical oddities in the pattern of the wrinkles have also been proposed as potential evidence for such a multiversal structure. Of course, this is an extraordinarily difficult claim to prove. The signal would be incredibly subtle, and other, less exotic explanations for these features are always possible. But the very fact that we can pose the question, and that our most precise map of the ancient sky holds patterns we can scrutinize for such an otherworldly signature, is profound. The cosmic microwave background, the afterglow of our own birth, might just contain the faded fingerprint of a cosmic neighbor we will never otherwise know. It transforms the sky from a ceiling into a possible membrane, a wall upon which the shadows of other worlds might be cast. That fading fingerprint of another reality is a ghost we may never fully capture, but the quest to map every subtle detail of our own universe's birth has never been more urgent. The cosmic microwave background is not a static picture we finished developing long ago. It is a portrait we are constantly refining, with each new generation of telescopes revealing finer brushstrokes and hidden colors in the canvas of creation. Our journey began with a blurry impression. NASA's COB satellite, launched in 1989, gave us our first glimpse of the wrinkles, transforming the uniform hiss into a mottled sky. It was like seeing the outline of a continent from a high-altitude balloon. Then came the Wilkinson Microwave Anisotropy Probe, WMAP, which spent 9 years staring at the sky from a stable point a million miles from Earth. It turned that outline into a detailed topographic map, measuring the temperature differences with such precision that we could read the universe's recipe, its age, and its geometry from the patterns. But the true masterpiece arrived with the Planck satellite, a European Space Agency mission that operated from 2009 to 2013. Planck's instruments were so sensitive they could detect temperature variations of a few millionths of a degree. The map it produced is the sharpest, most exquisite baby picture of the universe we have ever taken, a high-definition portrait of infant cosmos that has become the gold standard for cosmology. Yet even Planck's vision has limits. It saw the ancient light in incredible detail, but the next frontier is not just temperature, it is polarization. Think of light as a wave that can wiggle in specific directions. The cosmic microwave background light is polarized in subtle ways, a result of how it scattered off electrons in that primordial plasma. This polarization holds two types of patterns. The first, called E-mode polarization, has been mapped and confirms our standard story beautifully, but the second, B-mode polarization, is the holy grail. This faint, swirling pattern in the light's orientation could be the direct imprint of primordial gravitational waves, the space-time ripples generated by cosmic inflation in the universe's first violent fraction of a second. Finding it would be like hearing the echo of the Big Bang's shout rather than just seeing its afterglow. To hunt for this incredibly subtle signal, a new generation of observatories is rising. On the high, dry plateau of the Atacama Desert in Chile, the Simons Observatory is under construction. This ambitious ground-based project will deploy an army of small, ultra-sensitive telescopes, scanning the sky with a collective power far beyond any previous ground effort. Its goal is to measure the polarization of the cosmic microwave background with a precision that could finally detect the signature of those inflationary gravitational waves, or definitively rule out whole classes of theories. Looking further ahead, concepts for new space-based telescopes are already on drawing boards, designed to operate in the pristine quiet of space, free from Earth's atmospheric interference, to listen for this whisper from the very beginning. This relentless drive to map the unmapped to see the unseen is more than technical ambition. It is a direct line of inquiry back to our origin. Each new, more precise map is another page translated from the universe's autobiography, and we are just beginning to read its most profound chapter. That relentless drive to map the unseen brings us to the final, fundamental truth of this ancient light. The cosmic microwave background is not merely a fascinating relic, it is the bedrock upon which all of modern cosmology stands. It is the single most important piece of evidence we have for the Big Bang theory, the definitive signature that our universe had a hot, dense beginning. Without its faint, pervasive whisper, our story of cosmic origins would be a collection of intriguing ideas, but with it we have a witness. Every other observation, from the recession of galaxies to the abundance of light elements, fits into a framework validated by this primordial echo. It is the keystone in the arch of our understanding, the one piece that locks all others into place, but its role is far more active than that of a simple monument. The CMB provides the ultimate starting conditions for the universe. When cosmologists want to simulate the evolution of the cosmos, to watch galaxies form and clusters collide in their supercomputers, they cannot just start with random noise. They need a seed, a precise blueprint of the initial density fluctuations. They feed their virtual universes the exact pattern of hot and cold spots mapped by Planck and WMAP. From that specific, real data, the simulations unfold, showing how gravitational attraction amplifies those tiny wrinkles over billions of years into the cosmic web we observe today. It is the ultimate origin story coded into a dataset. Furthermore, this ancient light acts as a cosmic laboratory, constraining the fundamental parameters of reality with breathtaking precision. The exact statistics of its temperature fluctuations, the strength of its acoustic peaks, the pattern of its polarization, these are not just pretty pictures. They are a complex cosmic equation with one unique solution. By fitting our theoretical models to this data, we can read out the universe's age, its geometry, its total density, and the precise amounts of ordinary matter, and dark energy, all from a snapshot taken when it was an infant. The CMB has given us a complete quantitative recipe for the cosmos. Without this foundation, our understanding would be built on shifting sand, a collection of guesses about a past we could not verify. With it, we have a solid, data-rich bedrock. Yet, as we have seen, this very foundation is also what pushes us toward the edges of knowledge. The Hubble tension, the cold spot, the axis of evil, these are not failures of the model, but its greatest successes. They are the points where the data is so good, so precise, that it begins to reveal cracks in our current understanding, hinting at new physics waiting to be discovered. The cosmic microwave background is both our anchor and our compass, firmly grounding us in what we know, while its lingering mysteries point insistently toward what we have yet to learn. From a frustrating hiss mistaken for pigeon waste to the cornerstone of modern cosmology, our journey through the cosmic microwave background reveals a story of human curiosity at its best. This ancient light is far more than a static fossil on a museum shelf. It is a dynamic, living data set, a conversation with the universe that is still ongoing. Each new, more precise measurement refines our cosmic recipe, while its lingering anomalies like the Hubble tension and the cold spot actively challenge us to think bigger. They are not failures, but invitations to a deeper truth. So the next time you encounter the gentle crackle of an untuned radio or the grainy static on an old screen, pause for a moment. In that mundane noise, there persists the faint, cold whisper of creation itself, a 13.8 billion-year-old echo that is still telling us its secrets. We would love to hear which fact from this exploration resonated most with you. Was it the accidental discovery, the blueprint for all structure, or the haunting possibility of a multiversal bruise? Let us know in the comments below. If you enjoyed this deep dive into the universe's oldest light, be sure to subscribe for more journeys to the heart of space's greatest mysteries.